Hello everyone. Welcome to the training presentation from CERT, where we'll be diving into the explainable AI tools developed in Task 4.2 of Atlantis. We will explore definitions and objectives of XAI, discuss evaluation criteria for explainability, and examine a partial taxonomy used to design our XAI tools. These design criteria are informed by insights gained from deploying XAI in critical infrastructure protection. Finally, we will provide an overview of the current state of the XAI toolkit in Atlantis. Sometimes, the terms interpretability and explainability are used interchangeably in the AI landscape, both referring to the degree to which a human can understand the decision-making process of an AI system. However, upon closer examination, interpretability is typically defined with specialists and domain experts in mind, while explainability aims to serve a broader audience. It seeks to present, in a human-readable format, how and why the AI model reached a decision. Typically, XAI is employed to justify models' decisions, control and improve them throughout the development and deployment process, and gain insights into hidden facets of both the models and the available data. Specifically within Atlantis, we utilize XAI methods to anticipate emerging risks and present them in an easily understandable format. This facilitates the acceptance of AI decisions by end users and critical infrastructure operators, fostering well-coordinated collaboration between cyber and physical infrastructures. Unfortunately, there are no universally accepted evaluation criteria for explainability. However, we have identified some common qualitative and quantitative indicators prevalent in this domain, among which fidelity and stability stand out. Particularly in security-related domains, sparsity plays a crucial role. A large volume of alerts and corresponding explanations can obscure the end user's overview of the situational picture, hindering fast and targeted intervention from the CI operator. For a closer look, you can refer to the work we conducted within the context of Atlantis by scanning the QR code provided. Additionally, we developed a partial taxonomy of XAI to cluster and correlate XAI classes with their respective advantages and disadvantages concerning the quality of explanations, security, and privacy confidentiality. This work highlights that disclosing the decision-making process of an AI system can lead to privacy breaches, compromise confidentiality, and escalate security risks. It's crucial to consider this trade-off during the design process of XAI tools, in conjunction with stakeholders' requirements. Finally, let's examine the current state of the XAI toolkit in Atlantis. This component only has access to the inputs and outputs of the model and employs SHAP. Leveraging methods from game theory and existing XAI frameworks, SHAP balances between theoretical grounding and faster heuristic approaches with fewer guarantees. By doing so, SHAP manages to provide feature importance values for a dataset. Transitioning to the next component, this one requires access to certain model attributes, beyond just inputs and outputs. It is intended to provide higher quality explanations, but also presents higher security risks. This component utilizes GradCam, a gradient-based technique that leverages the backpropagation mechanism to assign importance values to input features, such as images, of a deep neural network. GradCam generates heat maps that highlight the regions contributing most to the model's decision-making process. Moving on to the next components, Explainable is an XAI technique that evaluates the impact of each neuron in a convolutional neural network on the decision-making process. P-Graph, on the other hand, is a visualization tool that represents nodes, such as neurons, using different colors and sizes according to specific attribute. Continuing with the next component, XAI for Rexy shows great promise as an end-to-end framework capable of handling multimodal data. It utilizes LIME to offer explanations on specific data points, SHAP for a comprehensive view of the entire dataset, and Llama to generate easily readable explanations for end users. Finally, the results from all these components are aggregated into a dashboard. Here, critical infrastructure owners and operators can review the processed outcomes and make decisions accordingly. This XAI dashboard can be integrated as a third-party component or a widget into a web page. Throughout this presentation, we've delved into the objectives, challenges, and implementation details of Explainable AI within the context of Atlantis. We've explored the development of XAI tools, shedding light on their crucial role in enhancing transparency and trust in AI systems, ultimately facilitating better collaboration between AI and CI operators. Thank you for your time and attention. Together, we're paving the way for a more transparent and collaborative future in AI, handling cyber and physical risks in the interconnected CI landscape of EU.